What if the entire universe was built from invisible bricks, smaller than anything we could ever see? What if every star, every planet, even you and I, were made from the same fundamental pieces? And what if, at the dawn of time, not a single one of them existed? The ship hums softly as it pierces the void, its frame trembling with anticipation. A crew, tense but determined, embarks on a voyage not across solar systems or galaxies, but into a realm far stranger. They are not astronauts, but atomonauts, explorers venturing into the heart of matter itself. Their mission, to traverse the inner architecture of the simplest atom in the universe, hydrogen. Departing from its solitary proton, they set out in search of the elusive electron that dances invisibly in the space around it. Unlike the moon-bound journeys of Apollo, which spanned mere tens of Earth diameters, this expedition covers a space unimaginably vast in relative scale, more than 63,000 times the width of their homeworld. But size is not the only strangeness. This isn't an orbit as Newton imagined, nor a path we can trace with certainty. In the quantum realm, the electron does not follow a neat trajectory. It exists in a haze of probability, a shimmering cloud of possibilities. To land is impossible, to locate is uncertain, and yet everything in the known universe is built from such mysteries. These atoms, tiny, unknowable, yet persistent, are the cosmic Lego bricks from which all structure arises. Stars, oceans, minds, and memories, all woven from these quantum whispers. And yet, at the very beginning, there were none. Not one atom stirred in the newborn cosmos. So where did they come from? How did something so fundamental emerge from a universe that began with nothing? Let us begin the smallest place imaginable to answer the biggest questions we've ever asked. The first light in the universe. Where did the first light come from? And what does it reveal about the birth of atoms, the fabric of our cosmos, and the nature of existence itself? A storm churns across the Black Sea. The tranquil surface, once a polished mirror to the sky, becomes a chaos of wind and wave. In the midst of this watery turmoil drifts a fragile kayak, barely more than a silhouette against the gray tumult. Inside it are two figures, a young physicist and his new bride. They are fugitives, not from war, but from an intellectual prison, fleeing a state increasingly hostile to curiosity, reason, and the pursuit of truth. The year is 1932. The physicist is George Gamov, born in Odessa, already known among European scientists for his brilliant theoretical insights. With him is Lyubov Volkmantseva, whom he affectionately calls Ro, after the Greek letter. Their union, both romantic and intellectual, is born under duress. In the Soviet Union, the winds have turned against scientists, with foreign ties or unconventional ideas. Travel abroad is tightly controlled. Gamov, eager to present his latest research at a conference in Rome, finds himself repeatedly stalled by Soviet bureaucracy. The passport office in Leningrad offers him no escape, only delay. But in that very same office, amid endless queues and shattered hopes, he meets Ro. They fall in love. They marry. And soon after, they make a bold and desperate decision to flee across the Black Sea and seek asylum in the West. Their plan is as daring as it is unlikely. They aim to reach Turkey by sea, navigating under cover of darkness, with only an old kayak and Gamov's Danish motorcycle license, acquired during his time with Niels Bohr in Copenhagen, as their hope for a plausible identity. The goal is simple: land on a Turkish beach, claim to be Danish, and plead for help from the Danish embassy in Istanbul. At first, nature is on their side. Calm waters, light winds. But by the second morning, the sea turns savage. A violent storm rises, and their fragile vessel is no match. Exhausted, delirious, they are cast adrift and blown back toward Crimea. their escape seems doomed. But eventually, with persistence and luck, they succeed. By 1934, they have left the Soviet Union behind for good, arriving in the United States, where Gamov would spend the rest of his life. And yet, the ideas born in his mind and the collaborations he would foster would help reshape our understanding of the entire universe. In the late 1920s, science was undergoing a revolution. Just 3 years before Gamov's escape, American astronomer Edwin Hubble had published findings that shook the foundations of astronomy. Galaxies, those distant glowing spirals, were not stationary. They were moving away from us, and not slowly. The further away they were, the faster they receded. If space itself was stretching, then it followed logically that the universe must have once been much smaller. Wind back time far enough, and every star, every planet, every atom must have been compressed into a single, unimaginably dense point. The idea would come to be known as the Big Bang, but in truth, it was not new to Gamov. Nearly a decade earlier, back in Leningrad, he had studied the equations of Alexander Friedmann, the Russian physicist who first derived a model of an expanding universe from Einstein's general relativity in 1925. The seeds of the Big Bang had been planted long before Hubble's observations. When Gamov arrived in America, his primary research interest was not cosmology, but the processes that power stars. Specifically, he was fascinated by nuclear fusion, the transformation of lighter atomic nuclei into heavier ones under immense pressure and temperature, releasing energy in the process. He understood that the same conditions that fuel the stars must once have existed throughout the entire cosmos long ago. In 1945, shortly after the end of World War II, Gamov began to connect the dots. He wrote to his old mentor, Niels Bohr, noting his growing interest in applying stellar physics to the conditions of the early universe. What if the entire cosmos, in its infancy, had once resembled the core of a star? Together with his student Ralph Alpher, Gamov developed a bold hypothesis that the early universe was hot, dense, and filled not with matter, but with radiation, specifically electromagnetic radiation. In their 1948 paper, often humorously referred to as the Alpha Beta Gamma paper, they proposed that shortly after the Big Bang, the universe was dominated not by atoms, but by light itself. This radiation, what physicists call electromagnetic energy, was not the kind of light our eyes are sensitive to. It spanned a vast spectrum, from high-frequency gamma rays to low-frequency microwaves. Just as there are sounds beyond the range of human hearing, so too there are wavelengths of light beyond our sight. But even though invisible to our eyes, this light held the power to shape matter. In the early universe, matter and light were inseparably intertwined. Photons, the particles of light, were trapped in a sea of charged particles, protons, electrons, and nuclei. The universe was opaque, like the interior of a star. Light could not travel freely. It bounced endlessly off charged particles in a chaotic dance. This era is sometimes called the photon epoch. It lasted for tens of thousands of years. During this time, matter was still forming, but radiation ruled. As the universe expanded, it cooled. Lower temperatures allowed protons and electrons to combine and form neutral hydrogen atoms, a process known as recombination. This is somewhat of a misnomer, as it was the first time these particles had ever combined in the universe. But the terminology stuck. With electrons now bound to protons, the universe became transparent for the first time. Photons were no longer scattered by free charges. They could finally move unimpeded, traveling vast distances without interruption. This release of photons, this first escape of light, is what we call the cosmic microwave background. Though we now detect it as faint microwave radiation, This light is a snapshot of the universe in its infancy, a moment frozen in time. It holds the patterns of tiny temperature fluctuations, the seeds of galaxies and cosmic structures that would form billions of years later. It is, quite literally, the first light of the cosmos. They also investigated what the early universe might have synthesized. Could all the elements we see today, carbon, oxygen, iron, have formed in that primordial fireball? Their conclusion was that only the lightest elements, hydrogen and helium, and trace amounts of lithium could have formed during the Big Bang. Heavier elements, they argued, must have been forged later, in the hearts of stars. This idea, now known as Big Bang nucleosynthesis, remains a pillar of modern cosmology. In those early dense epochs, the universe was dense enough for pressure waves, compressions, and rarefactions to ripple through it. These primordial sound waves, now stretched by billions of years of cosmic expansion, left their imprint on the large-scale structure of the universe. We call these patterns baryon acoustic oscillations. Though inaudible now, far below the threshold of human hearing, these waves can be detected through sophisticated surveys like the Sloan Digital Sky Survey. In a poetic gesture, physicist John G. Kramer even converted these ancient oscillations into audible sound using data from the early universe. The result? A deep, eerie rumble, a cosmic echo from the dawn of time. And so, from a stormy kayak voyage across the Black Sea to the luminous echoes of the Big Bang, we follow a thread of human curiosity that stretches across oceans, decades, and cosmic epochs. Gamov's life was emblematic of the power of science to transcend borders, political, geographical, and even temporal. His ideas helped illuminate the very origins of matter and light. The radiation that first poured across the newborn universe now bathes us from every direction, whispering the history of everything that has ever been. All of it, every star, every atom, every breath you take, can be traced back to those first few 100,000 years, to that light, to those waves, to the moment when the fog lifted and the universe opened its eyes. And all of it began with a question, not just where did everything come from, but how did the first light begin to shine? The weirdest object in the universe. Imagine yourself lost in a maze so dense, so impenetrable that every step forward ends in a wall. Turn left, dead end. Turn right, another. No landmarks, no pattern, no exit. Claustrophobia builds not from darkness, but from the realization that space itself offers no release. This was the condition of light in the earliest moments of the universe. In the seconds following the Big Bang, light was not the liberating, illuminating phenomenon we know. It was a prisoner of its own making, ensnared in a trap forged by its deep relationship with matter. Wherever photons tried to travel, they collided with a relentless soup of subatomic particles, bouncing, scattering, imprisoned. But to understand why light was caged, we must first understand what light is. Light, for all its elegance, is energy incarnate, a vibration in the fabric of the electromagnetic field. And energy, as Einstein taught us, is interchangeable with mass. In the high-energy furnace of the infant universe, light did what it could rarely do today. It shapeshifted into matter. Just fractions of a second after the universe was born, the searing temperatures reached over a quadrillion degrees. In these conditions, the energy of photons was so immense that light spontaneously transformed into particles, electrons, quarks, neutrinos, and their antimatter twins. Matter began to dominate the universe, but not yet in the form we recognize. At this stage, it was wild, chaotic, and unbound. To build atoms, those structured, composed units that underpin the universe, we needed more than just electrons. We needed protons, and for that, We needed something even more elementary: quarks. Quarks come in 6 varieties or flavors: up, down, charm, strange, top, and bottom. But only 2 are needed for the architecture of ordinary matter: up and down quarks. A proton is composed of 2 up quarks and 1 down quark, while a neutron is made of 1 up quark and 2 down quarks. These combinations sound simple, but the forces binding them are anything but. Quarks possess electric charge. Up quarks are positively charged, and down quarks are negatively charged. So how do 2 positive charges sit together within a proton without flying apart? The answer lies in one of the 4 fundamental forces of nature, the strong nuclear force. While gravity governs planets and stars, and electromagnetism dictates the behavior of light and charge, the strong nuclear force is the mighty glue that holds the nucleus of every atom together. It is, by every measure, the most powerful force known, 10 to the power of 38 times stronger than gravity. Yet this immense power comes with a caveat. It acts over vanishingly small distances, less than a trillionth of a millimeter. In the scorching, turbulent early universe, where particles zipped around with almost unimaginable kinetic energy, even this strong force was overwhelmed. Quarks could not bind into stable triplets like protons and neutrons. Not yet. Only when the universe had expanded and cooled for a millionth of a second did temperatures fall to about 1 trillion degrees. Then, and only then, could quarks be tamed into nucleons. The first protons and neutrons formed, stable, robust, and ready for the next stage in matter's long journey toward atoms. And yet, the story of the proton, far from being one of simplicity, is among the strangest in physics. Ask a physicist where a proton is, and they may smile ruefully. It's complicated, they'll say, because despite decades of investigation, the proton remains one of the most bizarre, elusive, and intricate objects in the universe. For one thing, the 3 valence quarks that compose the proton account for only 1% of its mass. The other 99% comes not from stuff in the traditional sense, but from a swirling storm of virtual particles and force carriers. Chief among them, the gluon. Gluons are the messengers of the strong nuclear force. They dart between quarks, binding them through a dance of continuous exchange. But unlike the photon, which carries the electromagnetic force without interacting with other photons, gluons interact with each other. This creates a tangled web of field interactions, spawning a sea of virtual particles. These sea quarks and their antiparticles briefly blink into existence within the proton. They borrow energy from the vacuum, just enough, just briefly enough, to satisfy quantum uncertainty. They annihilate and reform in a frenetic blur. The result is a particle that is more cloud than core, a restless, stormy sea of fluctuating mass and energy. In truth, the proton is less an object than a process, a bubbling, dynamic storm of quantum activity. Experiments like those at the relativistic Heavy Ion Collider, RIC in New York, have confirmed that the proton's mass is emergent. It arises not from the mass of its constituents, but from the energy of their interactions. Even stranger, these virtual sea quarks can include heavier varieties, like charm quarks, that are far more massive than the proton itself. A single charm quark has about 1.5 times the mass of the entire proton, yet they appear, briefly, without breaking the laws of conservation. This quantum weirdness, particles popping in and out of existence like flickering ghosts, doesn't just influence the proton, it defines it. Now that protons and neutrons exist, the universe's expansion continues. Particles slow, space cools, and a crucial window opens. Roughly 1 second after the Big Bang, the cosmos reaches a temperature of around 10 billion degrees. This is cool enough for protons and neutrons to begin binding together, held by the strong force, into simple nuclei, The first of these is the deuteron, composed of one proton and one neutron. It is the precursor to all heavier atomic nuclei. Enter George Gamov and his collaborator Ralph Alpher. In 1948, they published a groundbreaking paper, brief but revolutionary, in which they outlined the series of nuclear reactions that transformed the early universe's hydrogen into helium. This process, called Big Bang nucleosynthesis, took place within a 20-minute window. During this time, the conditions were just right for nuclear fusion to operate across the entire cosmos, just as it would billions of years later in the cores of stars. Through a rapid series of reactions, deuterons fused with additional protons and neutrons, creating helium-3, helium-4, and a trace of lithium. By the end of this short epoch, about 25% of the universe's mass was in helium nuclei. The remaining majority was hydrogen. But this was not yet the formation of atoms. What was created in the first 20 minutes were nuclei, the dense, positively charged cores of atoms. To complete the picture, they needed electrons. Electrons, lighter and more elusive than protons, had been present since the very beginning, but they roamed freely, constantly interacting with photons and other charged particles. Their journey into bound orbits required a universe that had cooled significantly more. The electromagnetic force, the one responsible for attracting negatively charged electrons to positively charged nuclei, is much weaker than the strong force. To give it a chance to bind electrons into orbits, the universe needed to cool to just 4,000 degrees Kelvin. That would take time. It was only then, in this cooler and more expanded cosmos, that electrons could finally settle into orbitals around nuclei, forming neutral atoms. This moment is called recombination, though in truth it was the first combination. With electrons now bound, photons were freed from constant scattering. Light, for the first time, could travel unimpeded. This release of photons is what we now observe as the cosmic microwave background, the afterglow of the Big Bang, stretched into microwaves by billions of years of cosmic expansion. It is the oldest light in the universe, a relic from a time when the first atoms were born. But even these electrons, the humble negative companions to protons, harbor strangeness. Electrons, as far as we can tell, are point particles. They have no internal structure, no spatial extent. They are, in the language of physics, truly fundamental, and yet they defy simple description. Electrons do not orbit nuclei in neat planetary tracks. Quantum mechanics tells us that such imagery is misleading. Instead, electrons exist as probability clouds, their positions uncertain, their velocities unknowable with precision. The Heisenberg uncertainty principle ensures that the best we can do is calculate the likelihood of finding an electron in a certain region. Moreover, electrons possess spin, a quantum property that defies classical analogy. Though we often describe it as rotation, this is a metaphor. Electrons do not spin in space. Yet their spin governs magnetic interactions and determines how electrons fill atomic orbitals, giving rise to the periodic table and the structure of matter. Spin half-particles like electrons also exhibit another counterintuitive behavior. They must rotate 720 degrees, not 360, to return to their original quantum state. This bizarre fact lies at the heart of quantum field theory and hints at the deep symmetries that underlie our universe. Thus, within every atom, within every breath of air, every drop of water, every star and cell and stone, is a swirling, probabilistic hall of mirrors, quarks that blink in and out of existence, gluons that bind the impossible, electrons that refuse to be pinned down. What seems so tangible and solid is built atop a bedrock of uncertainty and abstraction. And yet from this chaos, order emerges. Atoms became the building blocks of molecules, molecules the scaffolding for chemistry, chemistry the stage for biology. The structure of the universe, galaxies, stars, planets, people, flows from the first moment when light was set free by the formation of neutral atoms. In 1948, Ralph Alpher and Robert Herman predicted that the glow from that moment of release, the relic radiation of recombination, should still be visible. It would have cooled by now, they reasoned, stretched into microwaves. But their insight, profound as it was, went largely unnoticed for decades, until two radio astronomers working on a different problem in Holmdel, New Jersey, stumbled across a hiss that came from every corner of the sky. They had found the ghost of recombination, the first light, the proof that the universe began hot, dense, and full of potential. That light is still with us, whispering across the eons. It is the silent testimony of a time when the weirdest object in the universe, the atom, was first forged from light and fire. Seeing the Big Bang, a tale of invention, serendipity, and the echoes of creation. On a crisp September morning in 1941, a young Robert Dicks stood atop the radiation laboratory at the Massachusetts Institute of Technology, cradling a device of his own design. At just 25 years old, fresh from completing his PhD, Dick was already making waves. Yet few could foresee how his curiosity, first sparked by war, then stoked by wonder, would help reveal the earliest light in the universe. Dick's arrival at MIT coincided with one of the most pivotal moments in modern history. The world was already 2 years into the Second World War, and while the United States had not yet joined the fight, preparations were underway. Within weeks of his arrival, Japan bombed Pearl Harbor, and the U.S. entered the conflict the very next day. This marked the beginning of Dick's career in wartime science, a crucible of innovation that would leave lasting imprints on both technology and cosmology. At MIT, Dick's task was urgent and critical: radar development. The term radar had only recently been coined by the U.S. Navy. The principle was simple yet powerful: emit bursts of radio waves and detect their echoes off distant objects, such as enemy aircraft. However, early radar systems were crude. Their long radio wavelengths meant the details they captured were limited, much like trying to perceive fine brushstrokes through frosted glass. Dicke, with his keen engineering instincts and flair for invention, turned his attention to microwaves. Unlike radio waves, microwaves have much shorter wavelengths. The advantage was clear: finer resolution and greater sensitivity. This led to one of Dicke's key wartime inventions, the Dicke radiometer, a device finely tuned to detect faint microwave signals with unprecedented precision. Yet for all his contributions to military technology, Dicke's mind often wandered skyward, beyond the threats of bombers and missiles. He began to wonder, were there signals, not of war, but of nature, coming from space? Were there whispers of ancient cosmic events hidden in the microwave part of the electromagnetic spectrum? This thought stayed with him, quietly simmering for over a decade. After the war, Dicke returned to academia, joining the faculty at Princeton University. There, he rekindled his interest in the cosmos and began to seriously consider one of the most profound questions in all of science. How did the universe begin? At the time, the Big Bang theory was gaining traction, but it was far from universally accepted. The idea that the universe originated from an unimaginably hot, dense state and had been expanding ever since was as philosophically jarring as it was scientifically compelling. How does something come from nothing? Was and remains a natural reaction to the theory. Dicke, never satisfied with easy answers, explored alternatives. He considered a cyclical universe, one that expands, slows, reverses, and collapses in a grand Big Crunch, only to explode once more in a renewed Big Bang. An eternal cosmic heartbeat. Within this framework, Dicke envisioned a dramatic phase in the universe's history. As the cosmos contracted, temperatures would skyrocket, reducing matter to a primordial soup of protons, electrons, and subatomic debris. This incandescence, a searing fireball of radiation and particles, would be the crucible from which the universe would be reborn. During the subsequent expansion, the fireball would cool, and conditions would again become favorable for atoms to form. This process, he reasoned, could leave behind a telltale sign, residual radiation from that fiery epoch, lingering like a ghost in the cosmos. Unbeknownst to Dicke at first, this idea was not entirely novel. As early as 1948, physicist George Gamov and his collaborators Ralph Alpher and Robert Herman had predicted just such a relic. They hypothesized that if the early universe had been hot and dense, it would have emitted thermal radiation, initially visible light, that would persist even today, albeit stretched by cosmic expansion into the microwave part of the spectrum. Dicke independently arrived at the same conclusion. Building on his deep knowledge of microwave detection, he proposed searching for this fireball radiation, a fossil echo of the universe's formative moments. He surmised that over the billions of years since its emission, this radiation would have been redshifted by the expansion of space, moving it from the visible into the microwave region. If it existed, it should still be detectable using the kind of instrumentation he had been refining for decades. He began preparing for the observation campaign in the early 1960s, assembling a team and designing equipment. But fate intervened. Just 45 miles away, in Holmdel, New Jersey, two radio astronomers, Arno Penzias and Robert Wilson, were working on a very different problem. They weren't hunting cosmic relics. Instead, they were trying to eliminate noise from their measurements of satellite signals, using the massive 6-meter Holmdel horn antenna at Bell Labs. The noise they encountered was persistent and puzzling, a steady isotropic hiss that refused to go away. They were meticulous in their troubleshooting. Local sources of interference were ruled out. They cooled their receiver to near absolute zero using liquid helium, eliminating thermal noise. Still, the signal remained. Eventually, they discovered a pair of pigeons had taken up residence in the antenna, leaving behind what they later described as white dielectric material. The pigeons were gently removed and relocated, only to return. Eventually, with regret, they were euthanized. The antenna was cleaned, but the hiss endured. The signal, it seemed, was coming from every direction in the sky. Confounded, Penzias reached out to colleagues for insight. One of those calls went to Robert Dicke. At that very moment, Dicke and his team were in the middle of planning their own search for the fireball radiation. When he heard what Penzias described, Dicke turned to his colleagues and said, simply, "Well, boys, we've been scooped." Penzias and Wilson had unwittingly detected the cosmic microwave background, the faint afterglow of the Big Bang, the exact signature Dicke had set out to find. Their serendipitous discovery, published alongside a companion theoretical paper from Dicke's group, confirmed one of the most profound predictions of modern cosmology. In 1978, Penzias and Wilson received the Nobel Prize in Physics. Dicke, Gamov, Alpher, and Herman would never claim that honor. Yet their contributions laid the foundation for what is now one of the cornerstones of cosmological science. The CMB is more than just a technical curiosity. It is a snapshot of the universe when it was just 380,000 years old, a newborn in cosmic terms. At that time, the universe had cooled enough for electrons and protons to combine into neutral hydrogen atoms, allowing light to travel freely for the first time. That light, now stretched into microwaves, fills the universe. If the universe were a 40-year-old human, the CMB is the equivalent of a photo taken in the first 10 hours of life, a baby picture of everything. Yet this image is not smooth. Embedded in the CMB are minute temperature fluctuations, tiny differences in density, that seeded the large-scale structure of the cosmos. Where there was slightly more matter, gravity pulled in more. amplifying the contrast. Over time, these regions became the galaxies, clusters, and filaments we observe today. These fluctuations also preserve the echoes of sound waves, pressure oscillations in the hot plasma of the early universe, known as baryon acoustic oscillations. Like ripples frozen in time, they mark the rhythmic pulse of the infant cosmos. Today, surveys such as the Dark Energy Survey in the Chilean Andes map the universe in stunning detail. They reveal a vast, web-like structure, superclusters of galaxies and immense voids, all tracing the patterns etched into the CMB nearly 14 billion years ago. The seeds of the present were sown in the earliest moments, and remarkably, you don't need a giant telescope to sense this ancient light. In the era before digital broadcasting, an old analog television set could detect it, tune between channels, and a portion of the static, the snow dancing across the screen, was the cosmic microwave background, whispering across time. This signal will outlast us. It will fade only after trillions of years of continued expansion, eventually stretched beyond detection. But for now, it remains a testament to a moment when atoms first formed, when the universe became transparent, and when the light of creation began its journey to us. It's tempting to think that atoms were an inevitable outcome, that in any universe filled with light and matter, they would naturally form. But this is far from certain. The conditions had to be just right. A slightly different rate of expansion, a different balance of forces, and atoms might never have formed. No stars, no galaxies, no life. The formation of the first atom wasn't a guarantee. It was a cosmic triumph, and the light from that triumph still surrounds us. Woven into the very fabric of space, it is the echo of a fireball that once lit up the universe and has never truly gone dark. Why atoms? Imagine, for a moment, standing blindfolded before 24 loaded rifles, their barrels aimed squarely at your chest. You hear the subtle metallic clicks as the triggers are drawn back. Feel the tension of your final breath and brace for oblivion. Then, miraculously, every single shot misses. Not one, not two, but all 24 projectiles fail to find their mark. You survive. This dramatic thought experiment, proposed by Canadian philosopher John Leslie in his 1989 book, Universes, serves as a powerful metaphor for the seemingly improbable circumstances that allow our universe to exist, and more specifically, to allow atoms to exist at all. Just as it only takes one bullet to end a life, it would take only a minuscule tweak in the laws of physics to snuff out the existence of atoms. Yet here we are, awash in a cosmos teeming with them. From the moment of its birth, 13.8 billion years ago, the universe has undergone an extraordinary transformation. It began as an almost unfathomably hot, dense, and chaotic state, devoid of any structure. Today, it contains more atoms than we could hope to count in trillions upon trillions of lifetimes. Atoms form the scaffolding of all matter, from the most distant galaxies to the neurons in your brain. We take them for granted, but their very existence is predicated upon a precise balance of cosmic parameters, each one tuned so delicately that even the slightest adjustment would obliterate this fragile architecture. Let us consider a metaphorical control panel covered with dials, sliders, and switches, each governing a fundamental property of the universe: the masses of subatomic particles, the strength of fundamental forces, the rate of cosmic expansion. Tinker even slightly with the settings on this cosmic console, and atoms, the bedrock of chemistry and biology, would unravel. One of the most crucial parameters is the ratio between the size of electron orbits and the size of the atomic nucleus. For an atom to be stable, electrons must orbit at distances far greater than the size of the nucleus. If the electromagnetic force were even slightly stronger, electrons would spiral inward, crashing into the nucleus like satellites burning up on atmospheric re-entry. If the force were weaker, electrons would escape altogether, leaving protons isolated and chemistry impossible. But it's not just electromagnetism. The strong nuclear force, which binds protons and neutrons within the nucleus, must also be precisely tuned. Weaken it by just a small fraction, about 9%, and it would be too feeble to hold protons and neutrons together in the simplest nucleus, the deuteron. No deuterons, no fusion in the early universe. Strengthen it by just 2%, and 2 protons could bind into a diproton, a particle never observed in nature. Such particles would have rapidly fused into helium during the Big Bang, depleting the universe's supply of hydrogen, the foundational element upon which stars and life depend. The degree of fine-tuning required is staggering. A physicist would say these forces are finely tuned, a term that belies the almost cosmic improbability of the settings being just right. This idea, now central to debates in cosmology and philosophy, was first articulated in a meaningful way by physicist Robert Dicke in 1961. He argued that the universe appears biophilic. Its parameters fall into a narrow range that permits life. But it isn't only the fundamental forces that are delicately arranged. Consider the masses of the particles themselves. The neutron is just slightly heavier than the proton, by about 1/7 of 1%. This small disparity is critical. Were the neutron lighter, it wouldn't decay, and the balance of matter in the universe would be entirely different. If it were much heavier, it wouldn't form stable nuclei at all. If the electron were heavier than the mass difference between proton and neutron, it could be captured by protons, transforming them into neutrons and disrupting atomic structure altogether. These masses depend in turn on the quarks that make up protons and neutrons. A proton is composed of 2 up quarks and 1 down quark, while a neutron contains 2 downs and 1 up. The down quark is slightly more massive than the up quark, a difference that tips the scales just enough to make the neutron heavier. Were this mass difference altered even slightly, the entire narrative of the universe would change. Neutrons could decay into protons in an uncontrolled manner. Deuterons would become unstable, and the formation of elements beyond hydrogen would be thwarted. No oxygen, no carbon, no periodic table. And yet, through a delicate interweaving of forces and particles, atoms came into being. Their progenitors, the quarks, gluons, electrons, emerged within microseconds of the Big Bang. Within minutes, protons and neutrons fused into simple nuclei. Hundreds of thousands of years later, these nuclei captured electrons to form neutral atoms. Stars lit up, forged heavier elements, and exploded them into space, seeding the cosmos with the raw ingredients for planets, oceans, and life. Such a tale naturally invites questions. Why is the universe so precisely arranged? Why does it permit atoms at all? Why do we find ourselves in a cosmos capable of not only building complex structures, but also of reflecting on its own origins? To explain this fine-tuning, scientists and philosophers have proposed 3 broad possibilities. The first is sheer chance. Perhaps we simply won the cosmic lottery. The parameters had to take some values, and by astronomical coincidence, they fell into the narrow range that permits atoms. This explanation is logically consistent, but emotionally unsatisfying to many. The odds of getting all the settings right are comparable to selecting a single star, the Sun, out of a bag containing every star in the observable universe. Possible? Yes. Likely? Hardly. The second possibility posits design. Perhaps some conscious agent, be it a deity or an advanced civilization, deliberately tuned the settings. The universe, in this view, is a kind of simulation, a grand design meant to host life. While this idea has intuitive appeal, especially in the wake of our own increasing prowess with simulations and artificial intelligence, it steps beyond the empirical into the metaphysical. The third explanation, and perhaps the most scientifically adventurous, is the multiverse. In this framework, our universe is but one of countless others, each with its own set of physical laws. These alternate universes could arise from different quantum fluctuations in a grand cosmic landscape, as suggested by theories like eternal inflation or string theory. In this view, all possible values of the dials are realized somewhere. Most of these universes are sterile, no atoms, no stars, no life. But a few, like ours, happen to have the right settings. And naturally, we find ourselves in one of those rare few where atoms exist, because only such a universe can produce observers to contemplate it. This line of reasoning is a form of the anthropic principle. It doesn't explain why the universe is finely tuned. It merely reframes the question. Out of all the possible cosmic realities, we could only ever exist in one that permits our existence. The idea of the multiverse remains speculative, but it's not without support. Observations of the cosmic microwave background, the afterglow of the Big Bang, suggest that inflation, a rapid expansion of the early universe, did occur. And in many versions of inflation, it never ends completely, giving rise to a branching tree of universes, each with different properties. Regardless of which explanation is correct, chance, design, or multiverse, the conclusion remains the same. The existence of atoms is astonishingly contingent. The conditions required for them to exist are so precise, so interdependent, that their presence in our universe is nothing short of a cosmic miracle. And what a journey those atoms have taken. Forged in the hearts of stars, they've been scattered across galaxies, gathered into planets, dissolved in oceans, and eventually woven into the complex biochemistry of life. Some of them now sit inside the neural circuits of your brain, enabling you to read and ponder these words. The atom, that most elementary unit of matter, is the cornerstone of a vast and intricate story. A story of precarious balances, improbable coincidences, and profound implications. It is the narrative thread that runs through physics, chemistry, biology, and consciousness itself. As we gaze deeper into the cosmos, as we delve further into the quantum realm, we are reminded again and again of how rare and precious our existence truly is. And perhaps, in the end, it is this very improbability that makes the story of atoms and the story of us so endlessly compelling.
Begin and where does it end? Could the very existence of life, stars, and galaxies hinge on a delicate cosmic imbalance? To understand why the universe as we know it exists, we must first unravel the principles of balance, principles that govern not just our world but the entire cosmos. The foundation of reality, as we understand it, relies on a principle as ancient as time itself, balance. Energy can neither be created nor destroyed, it simply changes form. For every action, there is a reaction. What goes in must come out. This principle, rooted in the conservation laws of physics, dictates the behavior of everything from atoms to galaxies. In the 17th century, Italian physician Santorio sought to explore balance within the human body. Driven by curiosity, he embarked on a decades-long experiment. For 30 years, he meticulously weighed every liquid and solid he consumed and every excretion he produced. He weighed himself before and after physical exertion, keeping a daily record of matter in, matter out. Yet, Santorio encountered a puzzling mystery. The mass of his excretions never matched the mass of his food and drink. It was as though the human body, like a campfire, consumed matter and left behind something far less substantial than what it had started with. Santorio's instincts were correct. Matter does not simply vanish. By the 18th century, natural philosophers proved that the total mass before and after a chemical reaction is conserved. This revelation illuminated the workings of metabolism and combustion. Whether breaking down food into fats, proteins, and sugars or burning wood into ash, carbon dioxide, and water, every chemical equation balanced out. Atoms merely rearranged themselves, ensuring that the total count remained constant. Yet, even as this principle held true for most reactions, the universe itself began to challenge its own rules. The sun, the very source of daylight, provided a paradoxical clue that balance might be more complex than it first appeared. In the 20th century, humanity unlocked the nuclear secrets of the atom. Deep within the sun's core, hydrogen nuclei fused to form helium, releasing immense energy in the process. However, the mass of the resulting helium is less than the combined mass of the original hydrogen. The reaction seemed unbalanced. Where had the missing mass gone? A young Swiss patent clerk, Albert Einstein, provided the answer with his revolutionary equation. Mass, Einstein revealed, is not an isolated property but a form of energy. The missing mass from the sun's reactions is converted into photons, the sunlight that illuminates our days. Balance, though subtle and transformed, is ultimately restored. If the universe tends toward balance, then why does it seem so profoundly unbalanced? Nearly everything we see, touch, and experience is made of matter. From the atoms in our bodies to the stars in distant galaxies, the universe is overwhelmingly composed of matter. Yet, for every particle of matter, there exists an almost identical counterpart, antimatter. Antimatter particles mirror their matter twins in mass but carry opposite charges. According to the laws of physics, the Big Bang should have produced equal amounts of matter and antimatter. When matter meets antimatter, the two annihilate each other, releasing pure energy. If the early universe began in perfect balance, with equal parts matter and antimatter, then why is there such an overwhelming abundance of matter today? Where has all the antimatter gone? The imbalance between matter and antimatter is one of the most profound mysteries of modern physics. Without this asymmetry, the universe would be a vastly different place. No stars would shine. No planets would form. No life would exist. The cosmos would be a void of light and structure, filled only with radiation from matter-antimatter annihilations. Yet, the observable universe defies this fate. Somehow, in the earliest moments after the Big Bang, a subtle asymmetry emerged. For every billion particles of antimatter, there was 1,000,000,001 particles of matter. The excess matter survived annihilation, seeding the formation of galaxies, stars, and planets. This imbalance, infinitesimally small yet cosmically significant, is the reason we are here. How did this imbalance arise? Scientists have proposed various mechanisms, including processes known as baryogenesis. These theories suggest that tiny differences in the behavior of matter and antimatter, governed by the weak nuclear force, could have tipped the scales. Experiments, such as those conducted at particle accelerators like CERN, continue to probe the fundamental properties of matter and antimatter, searching for clues to this cosmic puzzle. As we gaze into the night sky, the vastness of the universe confronts us with its apparent contradictions. A cosmos that began in perfect symmetry now teems with imbalance, its laws both balanced and unbalanced in ways that sustain complexity and life. This paradox lies at the heart of existence. Why does the universe appear so perfectly balanced at its inception, only to evolve into a realm where imbalance gives rise to structure, light, and life itself? The journey of antimatter, from theory to discovery. The story of antimatter is one of the most fascinating and fundamental chapters in the history of physics, intertwining theoretical breakthroughs with experimental triumphs. The most famous equation in physics encapsulates the relationship between mass and energy. In this equation, represents the ultimate speed limit of the universe, the speed of light traveling unimpeded through the vacuum of space. Simple in appearance, This equation underpins Einstein's theory of relativity, which reshaped humanity's understanding of space, time, and energy in the early 20th century. This era marked a revolution in physics, where concepts once unimaginable began to reveal the universe's secrets. Among the brilliant minds of this transformative period was Paul Dirac, a theoretical physicist from Bristol. Dirac's contributions would not only extend Einstein's insights but also uncover an entirely new realm of existence. Born in 1902, Paul Dirac's journey began with engineering studies before transitioning to mathematics, earning his PhD from Cambridge in 1926. Known for his precision in thought and speech, Dirac's retorts during lectures were as incisive as his scientific insights. To fellow physicist Niels Bohr, he once advised, "Never start a sentence without knowing the end of it." By the mid-1920s, quantum mechanics was revolutionizing our understanding of the subatomic world. Electrons and protons, the only known particles at the time, could be described both as particles and waves. In 1926, Erwin Schrödinger published his foundational equation describing quantum systems. Yet, as Dirac examined this new framework, he realized it was incomplete. Schrödinger's equation did not account for the effects of Einstein's relativity. Dirac set out to unify quantum mechanics and relativity. His work culminated in the Dirac equation, a more comprehensive mathematical description of particle behavior. Years later, when asked about his groundbreaking discovery, Dirac's response was characteristically succinct: "I found it beautiful." Dirac's equation revealed a startling implication. While electrons had been understood to exist only with positive energy, the mathematics suggested they could also possess negative energy. This posed a problem. If negative energy states existed, electrons should continuously spiral into them, emitting infinite amounts of light in the process. Clearly, this was not the case in the observable universe. To resolve this paradox, Dirac proposed the existence of a sea of negative energy states, later known as the Dirac sea. In this model, all negative energy states were already filled, preventing electrons from falling into them. However, if an electron were given enough energy, it could leap out of the Dirac sea, leaving behind a hole. This hole would behave like a particle with the same mass as an electron but with opposite charge, an anti-electron. In 1931, Dirac proposed the existence of antimatter. Initially, he speculated that the anti-electron might be the proton, which was already known to have a positive charge. However, the proton's much greater mass ruled out this possibility. Dirac's anti-electron, later called the positron, remained a theoretical prediction, awaiting experimental confirmation. While Dirac's equations laid the groundwork, it was Carl Anderson who provided the proof. In 1931, Anderson began studying cosmic rays, particles streaming across the universe, using a cloud chamber. This device, filled with water vapor, allowed charged particles to leave visible trails as they passed through. Anderson observed a trail that mirrored those of electrons but curved in the opposite direction under a magnetic field. This indicated a particle with the same mass as an electron but with a positive charge. In 1932, Anderson published his findings, naming the particle the positron. Dirac's theoretical antimatter had become a reality. The discovery of the positron marked the beginning of an era. While positrons could occasionally be found in cosmic rays, other antiparticles were far rarer. Physicists turned to particle accelerators to create antimatter artificially. By colliding particles at high speeds, they converted kinetic energy into mass, producing showers of particles and their corresponding antiparticles. In 1955, scientists at the Bevatron Accelerator at Lawrence Berkeley National Laboratory created the antiproton. A year later, they discovered the antineutron. These discoveries expanded the antimatter catalog and opened new avenues for research. However, creating an entire antiatom remained a daunting challenge. In 1995, nearly 4 decades after the discovery of the antiproton, researchers at CERN achieved a monumental breakthrough. Using the low-energy antiproton ring, they combined antiprotons with positrons to create 9 antihydrogen atoms. This marked the first time an antiatom had been synthesized in the laboratory. Further advancements came in the following decades. By 2010, CERN scientists had developed techniques to trap antihydrogen atoms for extended periods. These experiments allowed researchers to study the properties of antimatter in unprecedented detail. Their findings confirmed that antihydrogen behaved almost identically to regular hydrogen, including its interactions with light. Antimatter holds profound implications for our understanding of the universe. Dirac's work not only expanded the boundaries of quantum mechanics but also raised new questions about the nature of reality. If antimatter mirrors matter so perfectly, why does the observable universe contain so little of it? The apparent asymmetry between matter and antimatter remains one of the greatest mysteries in modern physics. Additionally, antimatter offers tantalizing possibilities for technology. In theory, matter-antimatter annihilation could provide an incredibly efficient energy source. However, the practical challenges of producing and storing antimatter on a large scale remain formidable. Paul Dirac's pursuit of beauty in mathematics led to one of the most significant discoveries in physics. From the theoretical prediction of the positron to the creation of antihydrogen, the story of antimatter exemplifies the interplay between theory and experiment. Nearly a century after Dirac's groundbreaking work, his insights continue to inspire scientists, inviting us to explore the boundaries of the known universe and the mysteries that lie beyond. Where is all the antimatter? Imagine a world where humanity harnesses the boundless power of antimatter. What do you see? Do you envision massive interstellar starships racing through the cosmos, expanding our reach to habitable worlds light years away? Extraterrestrial colonies braving harsh or Eden-like landscapes, staring out at twin suns setting on alien horizons? Or perhaps a far darker vision, desolation, the aftermath of an untamed technology, a power station explosion dwarfing Chernobyl and Fukushima, humanity's frailty magnified by mutual annihilation. These scenarios, both awe-inspiring and terrifying, stem from the immense potential of matter-antimatter reactions, the most fuel-efficient process known in physics. According to Einstein's famous equation, the annihilation of matter and antimatter results in the total conversion of mass into energy. Gram for gram, matter-antimatter annihilation releases energy over 100 times greater than nuclear reactions and 1 billion times more potent than burning fossil fuels. No other process in physics can surpass this efficiency. For now, antimatter propulsion systems, batteries, and warheads remain the stuff of science fiction. Producing and storing antimatter for practical use consumes far more energy than the antimatter itself could release, rendering it unfeasible as a fuel. However, even without imagining futuristic technologies, antimatter is already part of our present, woven into the tapestry of daily life and scientific exploration. In 1940, Canadian chemist Martin Kamen was working at the Berkeley Radiation Laboratory at the University of California. His goal was deceptively straightforward: to create a new isotope of carbon, the elemental backbone of all known life. Together with his colleague Sam Rubin, Kamen irradiated graphite samples, hoping to induce the formation of a previously unknown carbon isotope. For days, they worked tirelessly, with Kamen enduring sleepless nights. One fateful evening, after stepping out for fresh air, Kamen's disheveled appearance caught the attention of a patrolling policeman. Mistaken for an escaped convict involved in a local murder spree, he was detained. Once cleared, Kamen returned to his experiments and finally succeeded. He and Rubin had discovered carbon-14. Though rare in nature, carbon-14 has become a cornerstone of radiocarbon dating, enabling scientists to determine the ages of ancient organic materials. For every trillion carbon atoms in your body, one is carbon-14. Unlike stable isotopes, carbon-14 decays over time, a process that begins when an organism dies. By measuring the remaining carbon-14, scientists can estimate how long it has been since the organism last absorbed this isotope through respiration or consumption. The decay of carbon-14 is a process of balance known as beta decay. During this decay, a neutron transforms into a proton, emitting both an electron and an antineutrino. Similarly, the decay of potassium-40 within your body sometimes produces positrons, the antimatter counterpart of electrons, and neutrinos. This means that all life on Earth, including you, is a natural antimatter factory, generating particles that briefly exist before annihilating with their matter counterparts. The properties of positrons have profound medical applications. In the 1950s, scientists developed a groundbreaking imaging technique, positron emission tomography, PET. By injecting a radioactive tracer into the bloodstream, PET scans track the positrons emitted during decay. These positrons annihilate with electrons, producing pairs of photons with a unique energy signature. Detecting these photons allows for detailed imaging of the body, enabling the diagnosis of medical conditions and mapping of brain activity. PET scans have revolutionized our understanding of how the brain responds to stimuli, from admiring a sunset to listening to a story or gazing at the stars. Antimatter is not confined to our bodies or laboratories, it also exists across the cosmos. Violent astrophysical events, such as supernovae and the collisions of neutron stars, eject antimatter into space. In the 1970s, astronomers detected a cloud of positrons near the Milky Way's center. NASA's Compton Gamma Ray Observatory later discovered a fountain of antimatter stretching 3,000 light-years out of our galaxy. The origins of these phenomena remain mysterious, hinting at undiscovered processes in the universe. Despite its presence, the amount of antimatter detected is vastly smaller than the amount of matter in the universe. This imbalance is crucial to our existence. If matter and antimatter had been created in equal quantities during the Big Bang, they would have annihilated one another, leaving behind a cosmos devoid of stars, planets, and life. Yet the observable universe is overwhelmingly composed of matter, with antimatter largely absent. To understand this imbalance, we must journey back to the universe's infancy. In the moments following the Big Bang, matter and antimatter should have existed in perfect symmetry. But something broke this balance. Theorists propose mechanisms such as baryogenesis, where subtle differences in the behavior of matter and antimatter led to a tiny excess of matter. For every billion particles of antimatter, there was one extra particle of matter. This infinitesimal asymmetry allowed matter to survive, forming the galaxies, stars, and planets we see today. The origins of this asymmetry remain one of the greatest mysteries in physics. Experiments at facilities like CERN continue to probe the properties of antimatter, searching for clues to the processes that shaped our universe. As we deepen our understanding, the story of antimatter reminds us of the delicate balances that underpin existence, from the fleeting positrons within our bodies to the vast cosmic structures born from an ancient imbalance. In exploring antimatter, we do more than unravel the universe's mysteries, we confront the profound question of why we are here at all. The dawn of time, a universe born of imbalance. The mystery of why we exist, why matter triumphed over antimatter, is one of the most profound questions in cosmology, a story that begins in the smallest fraction of a second after time itself began. 1/trillionth of a second after the Big Bang, the universe was a roiling sea of unimaginable energy, with temperatures reaching 1,000,000 billion degrees Celsius. There was no matter, no atoms or particles to provide substance to the cosmos. Instead, there was light, energy, and the nascent forces that would govern reality. At this temperature, following the principle of mass-energy equivalence, the energy began to condense into particles. From this sea of energy emerged quarks and their antimatter counterparts, antiquarks. Each quark came into existence paired with an antiquark twin. Alongside them appeared gluons, the particles responsible for the strong nuclear force. In cooler conditions, these gluons would have the power to bind quarks together into protons and neutrons. But the universe at this stage was far too hot. In this primordial quark-gluon plasma, particles zipped around at incredible speeds, colliding and annihilating one another. When a quark encountered its antiquark counterpart, they annihilated, converting back into energy in the form of photons. This process, repeated countless times, created a near-total annihilation of both matter and antimatter. As the universe expanded and cooled, leptons, such as electrons and their antimatter equivalents, positrons, began to form alongside neutrinos and antineutrinos. However, with the falling temperatures, new quark-antiquark pairs could no longer spontaneously arise from the vacuum. The quarks that remained slowed enough for gluons to begin binding them together, forming hadrons, the composite particles that include protons and neutrons. Similarly, antiquarks formed antihadrons such as antiprotons and antineutrons. As hadrons and antihadrons emerged, they too began annihilating each other. Protons and antiprotons, neutrons and antineutrons collided, converting their mass into energy. By the time the universe was 1 second old, the annihilation was nearly complete. For every billion particles of matter, only one survived. The rest, along with their antimatter counterparts, had vanished, leaving behind a universe dominated by light and radiation. Around 100 seconds after the Big Bang, the universe had cooled sufficiently for nucleosynthesis to begin. Protons and neutrons started combining to form the first atomic nuclei, giving rise to the light elements, primarily hydrogen and helium. But this process would not have been possible without the tiny imbalance that left one particle of matter for every billion particles of antimatter. Without this asymmetry, the universe would have been an endless expanse of photons with no atoms, no stars, and no life. Why did matter triumph over antimatter? According to our understanding of the Big Bang, matter and antimatter should have been created in equal amounts, leading to their mutual annihilation. The fact that matter remains is a fundamental violation of balance in the universe. This asymmetry, though crucial to our existence, defies the symmetry expected by the laws of physics. One hypothesis suggests that there might be regions of the universe where antimatter dominates, forming anti-galaxies and anti-stars. Since the spectrum of light emitted by antimatter atoms is identical to that of their matter counterparts, anti-galaxies would be indistinguishable from ordinary galaxies through telescopes. However, intergalactic winds would inevitably carry regular matter into these regions, leading to annihilation events. Astronomers have yet to observe the distinctive light produced by such annihilations, casting doubt on the existence of large antimatter structures. Smaller antimatter objects, such as clusters of anti-stars, might persist, shedding antimatter particles that blend into cosmic rays. These signals, however, are faint and difficult to distinguish amid the noise of the universe's radiation. Most scientists now agree that the answer lies not in hidden antimatter galaxies but in a deeper asymmetry embedded in the laws of nature. The universe, it seems, may not have the perfect balance or symmetry that we once assumed. Processes such as CP violation, a phenomenon where certain particle interactions slightly favor matter over antimatter, could explain the observed imbalance. Experiments at particle accelerators like CERN continue to investigate these subtle asymmetries, offering glimpses into the mechanisms that shaped our universe. The dawn of time was a battleground, a cosmic war between matter and antimatter. From this struggle emerged a universe dominated by matter, where the tiniest imbalance allowed for the formation of stars, planets, and life. Though the reasons for this asymmetry remain elusive, they are a testament to the delicate interplay of forces and particles that define our reality. As we peer deeper into the origins of the universe, we are reminded of how close existence came to never happening at all. The survival of matter over antimatter is not just a scientific puzzle but a profound reminder of the fragile circumstances that make our existence possible. The answers to this enigma, when they come, will illuminate not only the nature of the cosmos but the very foundation of why we are here. An unbalanced cosmos, the journey to understanding asymmetry. What if the universe as we know it had been perfectly balanced? Would matter and antimatter have annihilated one another in the first moments of existence, leaving behind a cosmos devoid of stars, planets, and life? How did the scales tip so slightly, yet so profoundly, in favor of matter, allowing the universe to take shape? These questions have driven some of the most pivotal discoveries in physics, revealing a cosmos where balance is more elusive than it seems. In 1912, Chien-Shiung Wu was born in a small fishing town north of Shanghai. Unlike most Chinese girls of her time, she received a formal education, attending a school for young women founded by her father. Her brilliance in academics led her to graduate at the top of her class with a degree in physics from the National Central University in Nanjing. Encouraged by her mentor, Dr. Jing-Wei Gu, Wu emigrated to the United States in 1936 to continue her studies, earning her PhD from the University of California, Berkeley, in 1940. In 1944, she joined the Manhattan Project at Columbia University, applying her expertise in beta decay to wartime research. By the mid-1950s, she had become a U.S. citizen and a leading expert in nuclear physics. It was her mastery of beta decay that would lead her to challenge fundamental assumptions about the universe. Charge symmetry. This principle asserts that positive and negative charges are treated identically by the laws of physics. For instance, up quarks, positively charged, and down quarks, negatively charged, should behave identically in mass and in nuclear reactions. Parity symmetry, often associated with handedness, parity symmetry suggests that the universe has no inherent preference for left or right. A mirror reflection of a physical system should behave identically to the original system. Time symmetry. This principle dictates that the laws of physics remain unchanged if the direction of time is reversed, with particles flipping their speed and spin as if the universe were rewound. Together, these principles form the foundation of CPT symmetry. If CPT symmetry holds, the universe should behave identically even under transformations of charge, handedness, and time. But what if one of these principles were subtly broken? In 1956, theoretical physicists Chen-Ning Yang and Tsung-Dao Li proposed that parity symmetry might not hold for the weak nuclear force, a controversial idea at the time. Li approached Wu to discuss the possibility of designing an experiment to test this hypothesis. Wu proposed an ingenious method involving the radioactive isotope cobalt-60. Cobalt-60 decays via beta decay, emitting electrons and gamma rays. Wu's experiment cooled cobalt-60 atoms to extremely low temperatures and constrained them within a magnetic field. If parity symmetry were conserved, the emitted electrons would show no preferred direction, even when the magnetic field was reversed. However, Wu's team observed a clear asymmetry. More electrons were emitted against the magnetic field than along it. Nature, it seemed, could distinguish left from right. This groundbreaking discovery, published in December 1956, shattered the long-held assumption of parity symmetry in the weak nuclear force. The universe, at its most fundamental level, was not symmetric. Despite Wu's pivotal role, the 1957 Nobel Prize in Physics was awarded solely to Yang and Li. Nevertheless, Wu's contributions cemented her legacy as a trailblazer in nuclear physics. Wu's work was only the beginning. In subsequent decades, experiments revealed violations of CP symmetry, the combination of charge and parity, in the behavior of quarks and antiquarks. These discoveries showed that the universe treats matter and antimatter differently, albeit in extremely subtle ways. By the end of the 20th century, CP violation was well established, confirming that the cosmos is slightly unbalanced. Could CP violation explain why matter outnumbered antimatter in the early universe? The asymmetry observed in quarks and antiquarks, while significant, is not sufficient to account for the 1 in a billion excess of matter that remained after the Big Bang. Scientists have since turned their attention to other particles, particularly leptons and neutrinos. Neutrinos are among the most enigmatic particles in the universe. Nearly massless and barely interacting with matter, trillions pass through your body every second without a trace. Unlike other particles, neutrinos exhibit a curious asymmetry. All observed neutrinos are left-handed, while all antineutrinos are right-handed. This raises intriguing possibilities. Right-handed neutrinos. If right-handed neutrinos exist, they may have played a role in the early universe, decaying more often into matter than antimatter. Neutrinos as their own antiparticles. Alternatively, neutrinos might be their own antiparticles, capable of annihilating themselves under certain conditions. This property, if confirmed, could help explain the matter-antimatter imbalance. Current research at particle accelerators and neutrino observatories aims to uncover whether neutrinos violate CP symmetry. Preliminary results are promising but inconclusive. If neutrinos indeed favor matter over antimatter, they could provide the missing piece of the puzzle. Another intriguing hypothesis suggests that pockets of antimatter might still exist, isolated from the rest of the universe. Antimatter clusters, such as antistars, could persist in regions far from regular matter, avoiding annihilation. Instruments aboard the International Space Station, like the Alpha Magnetic Spectrometer, are searching for rare antimatter particles, such as Helium 3. By studying the abundance of antimatter in our cosmic neighborhood, scientists hope to extrapolate its presence across the universe. The universe's asymmetry is both its mystery and its salvation. Without the slight imbalance that favored matter over antimatter, the cosmos would be a sea of photons, devoid of stars, planets, and life. The discoveries of Chien-Shiung Wu and others have illuminated the subtle ways in which the universe defies symmetry, offering glimpses into the mechanisms that shaped our existence. As we continue to explore these mysteries, each new discovery brings us closer to understanding why matter prevailed and why we are here. The story of the universe's unbalanced nature is not just a tale of physics, but a profound reflection on the delicate conditions that make life possible.
The first second, a universe in the making. What can truly happen in just 1 second? Can an entire cosmos, vast, intricate, and ordered, emerge from near nothingness in a time frame so minuscule it barely registers in human perception? If a second is long enough for the birth of new stars and the deaths of old ones, is it also sufficient to set in motion the laws of physics, the fabric of space-time, and the foundations of all that exists? To human observers, a second is fleeting, 1.3 heartbeats, 6.3 liters of blood pumped through the body, for births, 2 deaths. Yet on a cosmic scale, within the same fraction of time, our planet moves 220 kilometers in its galactic orbit, the sun sheds 1 million tons of mass into space, and nearly 1,000 supernovae explode across the observable universe. Time is relative, and perception shapes its meaning. But is a single second truly enough to construct the framework of reality? While ancient civilizations such as the Sumerians and Babylonians devised numerical systems based on 60, and Egyptians counted finger joints to establish units of time, modern science has anchored the second to the fundamental behavior of matter. The universe itself has endured for approximately 436 quadrillion seconds since the Big Bang, but those immense spans of time are dwarfed by the infinitesimal scales at which the earliest moments of creation unfolded. In 2020, scientists at the German electron synchrotron observed the shortest measurable span of time, 247 zeptoseconds, or 1/4 of a billionth of a trillionth of a second, the time it takes for light to cross a single hydrogen molecule. There are 2,500 times more zeptoseconds in 1 second than there have been seconds since the universe began. If time can be broken into such unimaginably small increments, then even the briefest moment may hold the potential for profound transformation. And indeed, in that first second of existence, the universe underwent changes more dramatic than in the billions of years that followed. Within the first 10 superscript 3 seconds, the epoch of cosmic inflation unfolded, exponentially expanding space-time at speeds far surpassing that of light. Quantum fluctuations stretched across the cosmos, forming the seeds of the galaxies we see today. By 10 superscript 1 superscript 2 seconds, the fundamental forces, gravity, electromagnetism, and the strong and weak nuclear interactions began to decouple, shaping the universe's physical laws. And by the end of the first full second, the universe had cooled enough for protons and neutrons to stabilize, setting the stage for atomic nuclei to form. Thus, in the grand scheme of cosmic evolution, a second is not just long enough to build a universe, it is foundational. That first second encoded the structure of everything that would follow, from galaxies to planets to life itself. When seen from the right perspective, 1 second is not an instant, but an eternity. In the eastern United States, spanning 34,000 square kilometers and encompassing portions of West Virginia, and Maryland, lies a region of eerie and deliberate silence, the United States National Radio Quiet Zone. Within its carefully maintained boundaries, radio transmissions, Wi-Fi signals, and mobile networks are suppressed, making it an unrivaled sanctuary for radio astronomy. At the heart of this oasis stands the Green Bank Observatory in West Virginia, home to one of the world's most sophisticated radio telescopes. The deliberate exclusion of all sources of terrestrial radio noise makes Green Bank the ideal location to eavesdrop on the universe, capturing signals from the depths of space uncorrupted by human interference. For over 65 years, this observatory has played a crucial role in advancing our understanding of the cosmos, from the intricate dance of pulsars to the enigmatic search for extraterrestrial intelligence. In 2012, Green Bank made headlines once more. Astronomers detected a piercingly precise radio signal emanating from a location more than 4,500 light-years away in the constellation Camelopardalis, the Giraffe. This repeating pulse of high-speed radio emissions was intriguing, not for what it suggested, but for what it was not. Despite the sensational hopes often pinned on such detections, it was not the work of an alien civilization. Instead, it was the telltale signature of a neutron star, a celestial relic of unfathomable density and power. The newly identified neutron star, dubbed PSR J0740, was an extreme specimen, spinning 346 times per second and unleashing torrents of radio waves that intersected Earth with unwavering regularity. More astonishing was its mass. At 2.1 times that of our Sun, compressed into a sphere just 27 kilometers across, PSR J0740 was crowned the most massive neutron star ever observed. Neutron stars represent the densest form of matter known to exist outside of black holes. A single cubic centimeter of their substance, about the size of a sugar cube, weighs a staggering 10 trillion kilograms. To put this into perspective, a mere teaspoon of neutron star matter would outweigh 8,500 Great Pyramids of Giza combined. But even PSR J0740 has its limits. Should a neutron star exceed approximately 2.2 times the mass of our Sun, the relentless pull of gravity would collapse it further, crushing it into the singularity of a black hole, a region of space from which nothing, not even light, can escape. This threshold remains an area of intense research, as the physics governing such extreme states of matter is still incompletely understood. A neutron star is the compact remnant of a once massive star that has reached the final stage of its life cycle. When a star many times the mass of the Sun exhausts its nuclear fuel, it can no longer resist the overwhelming force of gravity. The core implodes under immense pressure, compressing protons and electrons into an undifferentiated sea of neutrons. The result is a structure so dense that atomic structures cease to exist. No empty space remains between particles, creating a material so incompressible that it is effectively the universe's ultimate solid. These stellar corpses emit radiation across the electromagnetic spectrum, but most notably, they beam radio waves from their magnetic poles as they rotate, pulses that can be detected by observatories like Green Bank. The discovery of PSR J0740 and similar neutron stars serves as a cosmic laboratory for probing the limits of physics. While black holes remain forever beyond the reach of observation, hidden behind the event horizon, neutron stars offer a rare glimpse into the physics of extreme matter, providing clues about the behavior of particles under conditions that cannot be replicated on Earth. The study of neutron stars mirrors the challenges faced in understanding the origin of the universe itself. As we push the boundaries of physics to explain these ultra-dense objects, we confront a similar dilemma when exploring the first moments after the Big Bang. The universe began 436 quadrillion seconds ago, or so we believe. The nature of this beginning, however, remains one of the most profound mysteries in cosmology. Did the cosmos explode into existence from an initial singularity? Was it the result of a previous universe's cyclical collapse? Or was it born from interactions within a multidimensional hyperspace, imperceptible to us? These questions remain unsettled, resting at the precarious intersection of physics and philosophy. From its inception, the universe was governed by incomprehensibly small timescales. The Planck time, the smallest meaningful unit of time, is a septillionth of a zeptosecond. It is at this scale that the universe's earliest history is written, yet beyond the grasp of direct observation. Space and time, in their infancy, were quantum phenomena, chaotic, uncertain, and fluctuating wildly. In this early epoch, the four fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were likely unified. As the cosmos expanded and cooled, these forces began to separate, an event known as spontaneous symmetry breaking. This process laid the foundation for everything that would follow, from the formation of elementary particles to the large-scale structure of the universe. After just 10 quadrillionths of a zeptosecond, a dramatic transformation occurred. The universe underwent cosmic inflation, an unimaginably rapid expansion, increasing in size by a factor of 10 in less than a trillionth of a second. This expansion was so extreme that quantum fluctuations were stretched to macroscopic scales, seeding the density variations that would later become galaxies. Cosmic inflation solved several long-standing cosmological puzzles. It explained why the universe appears remarkably homogeneous on large scales and why it has a nearly flat geometry. It also set the observable horizon, ensuring that some regions of space would forever remain beyond our reach. Following inflation, the universe settled into a more gradual expansion. The cooling cosmos allowed the formation of the first subatomic particles, which in turn combined into protons and neutrons. Matter and antimatter, created in nearly equal amounts, largely annihilated each other, but a tiny asymmetry favored matter, ensuring the existence of the material universe as we know it. After 1 second had elapsed, the universe had expanded to approximately 20 light years across. It was filled with an intense plasma of high-energy particles, still seething with radiation and turbulence. Yet this was also the moment when structure began to emerge. The fundamental ingredients of the cosmos, quarks, leptons, and photons, had stabilized enough to lay the groundwork for the formation of atoms, stars, and galaxies in the billions of years to come. This first second was pivotal. It determined the balance of elements, the density of the cosmos, and the initial conditions from which all cosmic evolution would follow. Had any of these factors been slightly different, our universe may have been unrecognizable, perhaps even incapable of supporting complex structures like galaxies, stars, or life itself. The universe remains a grand puzzle, an ever-growing enigma that challenges the limits of human knowledge. Whether studying the crushing density of neutron stars or the first instance after the Big Bang, we find ourselves balancing on the edge of what is knowable. Each new observation refines our understanding, yet also reveals deeper layers of mystery. Despite the vastness of our scientific progress, we are still only scratching the surface. Our models of neutron stars and the early universe rest on a delicate scaffolding of theoretical constructs, an intellectual house of cards where a single new discovery could shift the entire foundation. And yet, it is within this uncertainty that the beauty of discovery lies, the endless pursuit of understanding a cosmos that is as boundless as our imagination. The discovery of PSR J0740 and similar neutron stars serves as a cosmic laboratory for probing the limits of physics. while black holes remain forever beyond the reach of observation, hidden behind the event horizon. Neutron stars offer a rare glimpse into the physics of extreme matter, providing clues about the behavior of particles under conditions that cannot be replicated on Earth. The study of neutron stars mirrors the challenges faced in understanding the origin of the universe itself. As we push the boundaries of physics to explain these ultra-dense objects, we confront a similar dilemma when exploring the first moments after the Big Bang. The universe began 436 quadrillion seconds ago, or so we believe. The nature of this beginning, however, remains one of the most profound mysteries in cosmology. Did the cosmos explode into existence from an initial singularity? Was it the result of a previous universe's cyclical collapse? Or was it born from interactions within a multidimensional hyperspace, imperceptible to us? These questions remain unsettled, resting at the precarious intersection of physics and philosophy. From its inception, the universe was governed by incomprehensibly small timescales. The Planck time, the smallest meaningful unit of time, is a septillionth of a zeptosecond. It is at this scale that the universe's earliest history is written, yet beyond the grasp of direct observation. Space and time, in their infancy, were quantum phenomena, chaotic, uncertain, and fluctuating wildly. In this early epoch, the four fundamental forces of nature, gravity, electromagnetism, the weak nuclear force, and the strong nuclear force, were likely unified. As the cosmos expanded and cooled, these forces began to separate, an event known as spontaneous symmetry breaking. This process laid the foundation for everything that would follow, from the formation of elementary particles to the large-scale structure of the universe. After just 10 quadrillionths of a zeptosecond, a dramatic transformation occurred. The universe underwent cosmic inflation, an unimaginably rapid expansion, increasing in size by a factor of 10 in less than a trillionth of a second. This expansion was so extreme that quantum fluctuations were stretched to macroscopic scales, seeding the density variations that would later become galaxies. Cosmic inflation solved several long-standing cosmological puzzles. It explained why the universe appears remarkably homogeneous on large scales, and why it has a nearly flat geometry. It also set the observable horizon, ensuring that some regions of space would forever remain beyond our reach. Following inflation, the universe settled into a more gradual expansion. The cooling cosmos allowed the formation of the first subatomic particles, which in turn combined into protons and neutrons. Matter and antimatter, created in nearly equal amounts, largely annihilated each other, but a tiny asymmetry favored matter, ensuring the existence of the material universe as we know it. After 1 second had elapsed, the universe had expanded to approximately 20 light years across. It was filled with an intense plasma of high-energy particles, still seething with radiation and turbulence. Yet this was also the moment when structure began to emerge. The fundamental ingredients of the cosmos, quarks, leptons, and photons, had stabilized enough to lay the groundwork for the formation of atoms, stars, and galaxies in the billions of years to come. This first second was pivotal. It determined the balance of elements, the density of the cosmos, and the initial conditions from which all cosmic evolution would follow. Had any of these factors been slightly different, our universe may have been unrecognizable, perhaps even incapable of supporting complex structures like galaxies, stars, or life itself. The universe remains a grand puzzle, an ever-growing enigma that challenges the limits of human knowledge. Whether studying the crushing density of neutron stars or the first instance after the Big Bang, we find ourselves balancing on the edge of what is knowable. Each new observation refines our understanding, yet also reveals deeper layers of mystery. The genesis of a universe, a tale of elements and discovery. On April 1st, 1948, the scientific journal Physical Review published a paper that would etch its place in history, not solely for its scientific contributions, but also for an unexpected twist of academic humor. Ralph Alpher, a dedicated PhD student at Johns Hopkins University, had spent a year meticulously developing a theory on the formation of the universe's chemical elements, working alongside his advisor, George Gamov. Yet, at the last moment, Gamov made a spontaneous and rather whimsical decision. He invited the esteemed physicist Hans Bethe to co-author the paper, despite Bethe having no direct involvement in the research. The motivation behind this peculiar addition: a perfect play on the Greek alphabet, forming the sequence alpha, beta, gamma. This seminal work, officially titled The Origin of Chemical Elements, became widely known as the Alpha-Beta-Gamma paper, or more simply, the alphabetical article. Alpher was understandably less than amused by the inclusion of Bethe, who had no hand in developing the theoretical framework. However, Bethe engaged in subsequent discussions and lent his expertise as nuclear physics evolved. Ironically, when new observational data emerged that challenged the original hypothesis, Bethe reportedly joked about changing his name to Zacharias to distance himself from the faltering theory. Alpher's theory was conceptually elegant. He proposed that all naturally occurring elements were assembled in the early moments of the universe through a successive process of neutron capture, forming progressively larger atomic nuclei. This framework provided a compelling explanation for the observed distribution of elements, wherein lighter atoms were significantly more abundant than their heavier counterparts. Mathematically, the model appeared sound. However, a fundamental problem arose, an issue that would ultimately unravel the entire theory. When scientists examined the known elements and their isotopic compositions, they found a conspicuous gap. There were no stable nuclei with atomic masses of 5 or 8. Nature provides us with helium, 4, lithium, 7, and beryllium, 9, yet no stable configurations exist with masses of 5 or 8. This discontinuity in the atomic mass spectrum posed an insurmountable challenge to Alpher's stepwise assembly model. Much like attempting to climb a staircase with 2 critical steps missing, nature simply did not provide a pathway for element formation through this process. To understand how the universe's modern chemical inventory came to be, one must first consider its constituents. On Earth, we find 92 naturally occurring elements, each defined by its unique number of protons. Many elements also have multiple isotopes, characterized by varying numbers of neutrons, influencing their stability over time. At the simplest end of the spectrum, we have hydrogen, an atom consisting of just a single proton, while at the heavier extreme lies uranium, 238, boasting 92 protons and 146 neutrons. Beyond Earth, astronomers have tirelessly cataloged the compositions of celestial bodies, ranging from the Sun and other stars to distant exoplanets, nebulae, and intergalactic dust. Their collective findings reveal an astonishing truth: the fundamental ingredients of the cosmos remain the same across the universe. Regardless of location, from the frigid edges of our solar system to the heart of a distant galaxy, the same 92 elements dominate the cosmic landscape. Yet, there is an intriguing variation in how these elements are distributed. Within our own solar system, the Sun holds the vast majority of hydrogen and helium, while heavier elements cluster closer to the star, forming rocky planets like Earth and Venus. On a larger scale, we observe that as one ventures toward the galactic core, the abundance of heavier elements increases. Conversely, long-lived stars such as red dwarfs, often found in the galaxy's outer reaches, contain fewer heavy elements, a reflection of their ancient origins before widespread stellar evolution had enriched the cosmos. These observations lead to a profound realization: the distribution of elements is directly linked to the life cycles of stars. In the densely packed, chaotic regions near a galaxy's core, gravitational forces continuously churn interstellar matter, forging new stars in turbulent bursts of formation. These stars, burning intensely hot and fast, rapidly consume their nuclear fuel before meeting their fate in cataclysmic explosions, supernovae that scatter their enriched contents back into the cosmic medium, seeding the next generation of stellar formations. In contrast, stars formed in the quieter outer reaches of the galaxy tend to burn cooler and live far longer. These stars, particularly ancient red dwarfs, offer a glimpse into the elemental makeup of the universe in its infancy, an era before successive generations of stellar birth and death had built up the heavier elements we find in abundance today. It was Hans Bethe, the unintended co-author of the alphabetical article, who further refined our understanding of this process throughout the 1950s and 1960s. He advanced nuclear fusion models that explained how elements from lithium to uranium are synthesized within the fiery cores of stars. His work, rooted in rigorous mathematics and bolstered by astronomical observations, withstood decades of scrutiny. In 1967, Bethe was awarded the Nobel Prize in Physics for his groundbreaking insights into stellar nucleosynthesis, a poetic twist given his incidental association with a paper that had so spectacularly misfired. While stellar nucleosynthesis accounts for the formation of most elements, it leaves a crucial question unanswered. Where did the lightest elements, hydrogen and helium, originate? These elements predate even the oldest stars, suggesting they were forged by an entirely different mechanism, one shaped not by the internal furnaces of stars, but by the fundamental conditions of the universe itself in its first moments. Though the alphabetical article ultimately failed to explain the formation of most elements, it was remarkably prescient in one regard: the origins of hydrogen and helium. These primordial elements must have been synthesized in an environment vastly different from that of stars, a state of the universe dictated by its infancy. As our understanding of cosmology deepened, it became clear that their creation was intimately tied to the physics of the Big Bang, the very moment when the universe itself was born. The true story of element formation is thus a tale of both cosmic grandeur and scientific persistence. It is a story shaped not by the whims of alphabetical coincidence, but by the profound forces that have governed the universe from its very first second. And as we continue to unravel the mysteries of the cosmos, it is a testament to the unyielding pursuit of knowledge that defines the human spirit. A glimpse of creation, peering into the universe's earliest moments. Atop the windswept summit of Mauna Kea, under the crisp clarity of morning light, a constellation of smooth white domes stands sentinel over the heavens. These are not mere observatories. They are the guardians of cosmic knowledge, housing some of the most advanced telescopes in the world. Their location is no accident. Mauna Kea's lofty elevation, combined with its exceptionally dry atmosphere, grants astronomers an unparalleled view of the universe. Here, in this rarefied air, scientists vie for precious observation time on one of the 13 telescopes that crown the volcanic massif, each eager to unravel the secrets of the cosmos. In 2013, a trio of American astronomers, harnessing the formidable power of the 10-meter Keck telescope, turned their gaze towards the constellation Leo in search of quasars. These enigmatic, star-like beacons, among the brightest objects in the universe, are thought to be hyperluminous galaxies from the universe's infancy. But before they could locate their quarry, they stumbled upon something wholly unexpected: an ethereal cloud of gas, invisible to the naked eye, yet unmistakable in the Keck's powerful sensors. This dim, elusive cloud was not merely an obstruction, it was an artifact of a distant past. By analyzing the extent to which its light had been stretched and redshifted by cosmic expansion, the astronomers determined that it lay 11.6 billion light-years away. The implications were profound, since the further we peer into space, the further back in time we see. This meant that the cloud's light had begun its journey a staggering 11.6 billion years ago, when the universe itself was less than 2 billion years old. We have long observed stars and galaxies at such vast distances, confirming that by this epoch, the universe had fully entered its age of starlight. Yet when the astronomers scrutinized the composition of this ancient cloud, they found a striking simplicity. It was composed solely of hydrogen and helium. Intergalactic gas clouds are not rare. Throughout the cosmos, they float within and between galaxies, enriched by the remnants of long-dead stars. The deaths of these stars, whether through gentle dispersal or cataclysmic supernovae, scatter heavier elements like carbon, oxygen, and iron into the void. These elements, in turn, seed the birth of new stars, planets, and moons. But these newly discovered clouds bore no trace of heavier elements. Their purity was untainted by the cycle of stellar birth and death. The realization dawned. These clouds were pristine relics of the universe in its earliest moments. They had never been touched by fusion, never witnessed the ignition of stars. Against all odds, these isolated patches of space had remained chemically unchanged since just 1 second after the Big Bang. The story these clouds tell is one of survival and primordial origins. Their light, captured by Keck's telescopes atop Mauna Kea, paints a picture of the cosmos as it was a single second after its inception. By this moment in time, the universe had undergone a profound transformation. Initially, the cosmos had been an unfathomably hot, dense, and indistinct plasma, a turbulent sea of energy and fundamental particles. Yet, even in this chaos, the universe was already undergoing rapid expansion. By the time it reached the 1 second mark, it had cooled to a still staggering temperature of about 10 billion Kelvin and had expanded to span several light years across. This was a universe in flux. Subatomic particles were locked in an intricate dance of annihilation and survival, shaped by the laws of physics as we understand them today. The Higgs field had already endowed particles with mass, distinguishing them from the sea of energy that had preceded them. The four fundamental forces, gravity, electromagnetism, and the strong and weak nuclear forces, were in full operation, though their behavior in this extreme environment was markedly different from what we observe today. Then, within this fleeting cosmic moment, an event occurred that would set the foundation for all that followed. It was here, in this seething maelstrom of energy and matter, that the first atomic nuclei began to form. As the universe expanded and cooled further, protons and neutrons fused together in nuclear reactions that laid the groundwork for the simplest and most abundant elements, hydrogen and helium. The hydrogen and helium clouds discovered in 2013 are direct descendants of this epoch. Untouched by the passage of time, they represent the universe before stars, before galaxies, before complexity. They are echoes of a moment when the cosmos was still forging its fundamental building blocks. As their light reaches the Earth's summit observatories, they offer us an unprecedented glimpse into the infancy of the universe. With each photon captured, we refine our understanding of the processes that govern the earliest seconds of existence. These ancient clouds serve as a reminder of the delicate interplay between fundamental physics and cosmic evolution, a story that began with a fraction of a second and has continued to shape the universe ever since. Through telescopes like Keck, and with the aid of new observatories such as the James Webb Space Telescope, we stand on the precipice of even deeper discoveries. As we probe further into the past, beyond the first stars and galaxies, we edge closer to the moment of cosmic birth itself. And in doing so, we continue humanity's timeless pursuit to understand not just the universe, but our place within it. A perfect balance, the cosmic role of helium and the fragility of creation. In August 1868, under the sweltering sun of Guntur, India, French astronomer Pierre Janssen stood with determination, his wide-brimmed hat offering little respite from the relentless heat. Around him, a gathering of curious locals, both adults and children, watched in bewilderment as he adjusted his telescope, its lens aimed directly at the burning disk of the sun. Many whispered among themselves, questioning the sanity of the perspiring foreigner. What secrets could he hope to uncover by staring at the very source of the day's unbearable warmth? But Janssen was no fool. He had journeyed over 6,000 miles from Paris, dedicating months of preparation for this singular moment. As he shaded his eyes and stole a glance upward, a familiar yet exhilarating sight met him. A tiny bite had been taken from the sun's edge. The eclipse had begun. As the moon's shadow crept over the solar disk, a chilling silence descended upon the land. Animals stirred uneasily. Cows let out low, confused moos, while birds flitted nervously from tree to tree. But for Janssen, the moment of totality was one of clarity and exhilaration. His telescope, carefully calibrated, now captured the ethereal glow of the solar corona, a luminous ring outlining the obscured sun. Janssen quickly turned his attention to his spectroscope. Though spectroscopy was still in its infancy, it had already proven itself an invaluable tool for identifying the composition of celestial bodies. Each chemical element, when heated, emits or absorbs light at distinct wavelengths, leaving behind a unique fingerprint. Scientists had already cataloged the spectral signatures of known elements: sodium, hydrogen, iron, and many others. But as Janssen analyzed the sun's corona, a new and unrecognized line of light stood out to him, a spectral signature that bore a resemblance to sodium, yet was distinct enough to indicate something entirely new. Days later, across the world in England, a second astronomer confirmed Janssen's observations. The mysterious spectral line belonged to an element never before seen on Earth. In honor of its solar origins, they named it helium after the Greek word helios, the sun. Despite its presence in the sun, many scientists remained skeptical of helium's existence. If this new element was so abundant in the cosmos, why had it never been found on Earth? The answer lay in helium's nature. Unlike most elements, helium is light, inert, and almost completely unreactive. When released into the atmosphere, it drifts upward, escaping into space, never binding to the rocks, minerals, or compounds that make up our terrestrial environment. This natural scarcity kept it hidden from earthly detection for decades. It was only in the early 20th century that prospectors searching for oil in Dexter, Kansas, unwittingly stumbled upon helium mixed within natural gas reserves. It turned out that certain underground geological formations could trap helium just as they did methane. This discovery transformed helium from a cosmic enigma into an invaluable industrial resource. Today, helium is not merely a party trick for filling balloons. Its unique properties, particularly its low boiling point, make it critical for cooling superconducting magnets in MRI machines, enabling deep-sea diving, and even fueling space exploration. Yet despite its importance, Earth's helium reserves remain finite. Every year, humanity consumes 140 billion liters of the gas, and once released, it is lost to space forever. While helium may be rare on Earth, it is the second most abundant element in the universe, making up nearly 25% of all matter. This extraordinary prevalence can be traced back to the first moments after the Big Bang. At the 1-second mark, the universe was a seething cauldron of energy and particles. Temperatures exceeded 10 billion Kelvin, and matter existed in the form of a hot plasma, a soup of quarks, electrons, and their antimatter counterparts. Amid this chaotic state, the fundamental forces of nature, gravity, electromagnetism, the strong nuclear force, and the weak nuclear force, began to govern the unfolding structure of the cosmos. As the universe expanded and cooled, quarks combined to form protons and neutrons. However, a fascinating and critical imbalance emerged. Protons and neutrons, though similar in structure, have a minute difference in mass, neutrons being about 0.1% heavier than protons. This seemingly trivial disparity had profound consequences. As the universe cooled further, free neutrons began to decay back into protons through the weak force. If left unchecked, all neutrons would have vanished within minutes, leaving behind a universe composed solely of protons. But before this could happen, some neutrons found sanctuary by binding with protons to form deuterium, also known as heavy hydrogen. These deuterium nuclei then fused into helium. Thus, helium became the first stable atomic nucleus formed in the cosmos, and its abundance was locked in forever. This process, known as Big Bang nucleosynthesis, dictated the elemental makeup of the early universe: 75% hydrogen, 25% helium, and trace amounts of lithium and beryllium. These primordial elements became the building blocks of stars, galaxies, and eventually life itself. But what if things had been different? What if the neutron-proton ratio had tilted in the other direction? Had neutrons been slightly lighter than protons instead of the other way around, the early universe would have produced far more neutrons than protons. The excess neutrons would have combined into helium, leaving no free protons behind to form hydrogen. Without hydrogen, the fuel for stellar fusion, no stars could have formed. No galaxies would have ignited. No heavy elements, carbon, oxygen, iron, would have emerged from dying stars. The universe would be a cold, dark expanse dominated by inert helium and lifeless neutron matter. The difference in mass between protons and neutrons, so small as to seem insignificant, determined whether a universe teeming with life could ever come to be. Scientists still lack a fundamental explanation for why protons are ever so slightly lighter than neutrons. It is a mystery etched into the very foundation of existence, a seemingly arbitrary quirk of physics that made all the difference. Today, from the summit of Mauna Kea, astronomers catch glimpses of these primordial processes. The same helium first formed in the Big Bang now glows in the distant light of ancient gas clouds near the constellation Leo, billions of light years away. These pristine relics of the early cosmos provide a direct link to the 1 second-old universe, a time when the delicate balance of fundamental forces determined the fate of everything that would follow. If helium had not formed in precisely the quantities it did, the cosmic story would be very different. But it did, and here we are. The history of the universe, from its fiery inception to the creation of galaxies, stars, and eventually life itself, hinges on the outcome of that fleeting moment. A second after the Big Bang, the blueprint for everything, the structure of stars, the chemistry of planets, and the emergence of life, was already in place. It was a perfect balance, an intricate interplay of cosmic forces that set the stage for the universe as we know it today.